In acoustics, there are two physical regions which are important for us to understand, the acoustic near field and far field. So with the sound source, obviously the near field means you're closer to your sound source, and the far field happens when you are further away. This transition between near and far happens at about one wavelength and extends to infinity once you're in the far field. In the near field, the sound energy is a bit more complicated. Right next to the vibrating surface of the sound source, the air molecules are actually sort of trapped and just circulate back and forth with that vibrating surface. And all of that sound energy is stuck right there. As we move a little bit further away, some of that sound energy begins to propagate, but some of it still circulates with that vibrating surface. This transition continues right up until the edge of the far field, where once you're in the far field, that sound energy just propagates away. And this happens at about one wavelength, or 3 times the largest dimension of your sound source. If you imagine a really large speaker versus a point source, that large speaker is going to have a bigger near field than just a small point source. So it's important to do a check and make sure you're in the near field or the far field. There's also the free field and diffuse field, and these are not properties of the source so much as the environment in which the source is. And so in the free field, this means that there are no objects for the sound to reflect off of. The sound energy leaves the sound source and propagates away forever. So if we make a measurement in the free field, the sound energy leaves the source, passes our microphone exactly once, and then never comes back. This makes a free field very appropriate for things like sound power measurements or sound source localization measurements, where we're trying to figure out where the sound came from. So this is either a large wide open space where there's no object to reflect off of, or we can simulate a free field by absorbing these sound waves. So if we treat the walls and ceiling of our room with highly absorptive material, we can prevent these reflections by absorbing the sound. That's an anechoic chamber. The opposite is if we take this sound source and we put it in a room with highly reflective walls. And often these walls are not even at right angles to encourage the sound to bounce around. So when the sound waves leave the sound source, they strike the wall and they bounce back. And in this simple illustration here, I've only included a single reflection. In reality, even these reflected waves would then bounce and continue to reflect all the way around. But even with this simplified illustration, you can see how complex the sound field gets. And this makes what we call a diffuse field, where there's nothing but reflections. With so many reflections going on, it's impossible for us to tell where the sound came from. So if we had a sound intensity probe, which measures the magnitude and direction of sound flow, we would measure zero intensity, because all of the sound is just sort of from everywhere. This property of a sort of a homogeneous, even sound field is used to our advantage. Often in partnership with that free field, we can measure things like absorption of materials or sound transmission loss of barriers and things like that. So that's a diffuse field.